Hey everyone, welcome to this explainer. Today, we're taking those abstract, jumbled up letters and numbers you see on a chalkboard and finally making sense of them. We're going to completely demystify linear equations. Because let's be real, memorizing formulas like y equals mx plus b without knowing what they actually do is incredibly frustrating. So we're going to translate these concepts into a totally relatable real-world scenario. By the end of this, that famous equation won't just be something you temporarily memorize for a test. It'll be an intuitive tool you actually understand. Let's jump right in. So here's our game plan for today. We'll start with the definition of slope, then move on to calculating and categorizing different slopes. After that, we're building the slope-intercept form, graphing and verifying some points, addressing a pretty common domain misconception, and finally doing a quick recap and knowledge transfer. All right, part 1, the definition of slope. Let's kick things off with the strict mathematical definition. Slope is literally just the vertical change divided by the horizontal change between any two distinct points on a line. If you're looking at a coordinate plane, this is exactly how we measure steepness. You've probably heard the phrase rise over run, right? It tells us exactly how much our output, or y-coordinate, rises or falls for every single unit our input, the x-coordinate, runs horizontally. Getting a grip on this one concept is the absolute key to unlocking almost all of linear algebra. But let's actually bring that abstract definition to life. Think about the physical world. Like, imagine you're sitting in the back of a taxi cab, just watching the meter tick up. In that context, slope is simply a constant rate of change with attached units. It's not just some random floating math number, it's super concrete, like dollars per mile. So in our taxi model, every time the car travels one horizontal mile, that's our run, the cost rises vertically by, let's say, $2.50. That's our rise. When you think of slope as a physical rate with real units, the math just kind of clicks. Moving on to section 2, calculating and categorizing slopes. So how do we actually calculate this from real data? Let's extract the slope from a standard table of values. Take a look at these two data points from our taxi ride. At 2 miles, the cost is $8. At 4 miles, it's $13. To compute the slope, we find the difference in our cost, the vertical change, and divide it by the difference in our miles, the horizontal change. The cost goes from 8 to 13, which is an increase of exactly $5. The distance goes from 2 to 4, so an increase of 2 miles. $5 divided by 2 miles gives us our constant rate of change, $2.50 per mile. Boom! We just calculated slope using nothing but basic subtraction and division. Now, depending on the scenario, slopes are going to fall into one of 4 distinct visual categories. First, you've got a positive slope. This looks like a line going uphill from left to right, just like our increasing taxi cost. Then there's the negative slope, going downhill, representing a decreasing value over time. Next is a zero slope. This is a perfectly horizontal line, kind of like walking steadily on completely flat ground. And finally, an undefined slope. This is a perfectly vertical line, straight up and down, literally like falling off a cliff. This vertical drop happens when your horizontal change is 0, and as we know in math, trying to divide any number by 0 is completely impossible. Let's pause for a quick knowledge check before we move forward. Think about this for a second. If your taxi charged a flat fee, say $15 no matter if you traveled 1 mile or 100 miles, which of those 4 slopes would perfectly represent your ride? Well, if the cost never rises, the vertical change is exactly 0. So this would be a zero slope, a perfectly flat horizontal line right across your coordinate plane. All right, part 3, building slope-intercept form. Now we get to the famous mathematical equation, y equals mx plus b. Let's compare that directly to our taxi context, where cost equals the rate times miles plus the initial fee. This maps the abstract algebra beautifully to our real-world scenario. The m in our equation is the mathematical slope, which we now know is our constant rate of $2.50 per mile. The x is our input, meaning the miles driven. And what about that b? That is our y-intercept. In the real world, b is the initial fee you're charged, just for sitting in the cab, before you've traveled a single mile. Every variable literally has a distinct real-world job. Next up, section 4, graphing and verifying points. Okay, so how do we take this equation and turn it into a clear visual graph? It's a simple 3-step process. Step 1, start by anchoring your y-intercept, that b value, right on the vertical y-axis. This means your starting point is at the exact coordinate 0, b. For our taxi, this represents 0 miles driven. It's the exact moment you close the door and the meter locks in that initial base fee. Step 2, use your slope, the m, to find your next point by counting the vertical rise and horizontal run. So up $2.50 and over 1 mile. Finally, step 3, simply draw a straight, continuous line connecting and extending through your points. But here's the cool part. Once we have an equation and a graph, we don't just have to guess if our line is drawn accurately, we can systematically and mathematically verify it. We do this by substituting coordinate values back into our equation to see if both sides balance perfectly. So let's say our initial fee, our b value, was exactly $3. This means our equation is y equals 2.50 times x plus 3. Let's see how we can use this to actually prove our graph is correct. Time for our second check. Let's figure out if a 3-mile ride actually costs $10.50 based on our established equation. If we plug in 3 for our x input miles, we calculate $2.50 times 3, which comes out to $7.50. Then we add our $3 initial fee, and we get exactly $10.50. The left side equals the right side. This perfect mathematical balance definitively proves that the point 3:10:50 sits perfectly on our graphed line. How satisfying is that? Let's dive into Section 5, the domain misconception. Okay, here is a really crucial mathematical pitfall we need to talk about. We have to correct the misconception that b is always a meaningful starting value outside the context domain. See, a theoretical mathematical line, the kind with arrows on both ends, extends infinitely in both directions. However, the domain, which is the set of all possible valid input values, actually has to make sense in context. Extending our taxi model to the left of the y-axis makes absolutely no physical sense. Why? Well, because you literally can't drive negative miles. So while b is a mathematically valid starting value on the y-axis, the line practically does not exist for negative x values outside of our logical context domain. And finally, Section 6, recap and knowledge transfer. We have covered a tremendous amount of ground today, analyzing inputs, outputs, constant rates of change, and domain restrictions. So let's lock in the major takeaways. First, slope is simply vertical change divided by horizontal change. It acts as a practical rate with units attached. Second, the equation y equals mx plus b is a super powerful tool to model linear relationships in the real world. The variable m is your constant rate of change, and b is your initial starting value, the y-intercept. But remember, that starting value only has physical meaning within the logical boundaries or the domain of your specific scenario. To wrap things up, I want to leave you with a final thought to really test your understanding. Try taking this algebraic framework we've just built and applying it to a totally new context. Imagine you have a plant that is currently 4 inches tall, and it grows at a steady rate of 1 inch a week. What are your m and b values for that equation? Think carefully about which number represents the starting point and which one represents the rate of change. Could you graph it? I'll leave you to solve that puzzle on your own. Thanks so much for joining me on this explainer, and keep looking for the math in the real world.